This is the second part of video lecture for week 12. Here we develop a method for computing the area beneath the graph of y equal to fx and above the x-axis in the interval a to b. This is what the graph. So this is y equal to fx above the x-axis and between the interval. What we do here is that we divide this whole interval into equal number of parts. That is, we partition it into regular partition, we call it. And the width of each subinterval, that is, this is here divided into 1, 2, 3, 4 subinterval, and width of this is given by b minus a divided by n. So b minus a divided by n will give you the width of each subinterval in the partition. And we denote the width of this each subinterval, which is equal, by delta x, meaning a small change in x. Then the points in the partition are denoted by first point x0 as a, x1 as x0 plus delta x, x2 as x1 plus delta x, and so on. So in general, we can write this as all the points in the partition. What we do after this, that we construct a rectangle of height fx on each subinterval. So you see we have 4 subintervals, 1, 2, 3, 4, and then we draw 4 rectangles on each subinterval. What we see here is that 2 of these rectangles, you see this and this rectangle, enclose more area than that under the curve, and 2 enclose less area on the whole. You see these 2 are covering going more and these 2 are covering less, but overall the effect of this is that, see that on the whole the sum of the areas of the 4 rectangle provides an approximation to the total area under the curve. That means finding the total area of all these 4 rectangles and finding the area of this area under this curve is almost same, because this more is what we call taken care by this thing. So what we can do is that area of each rectangle is height into width. So we add all. So here we have taken the 4 rectangle for this case. So we write in general, if we dividing the whole what we call interval a to b into n intervals, then area is given by this approximately, not exactly. Then we write this in the summation format. Summation I from 1 to n f of xi delta x. So finding the summation of this is nothing but finding the area of n rectangles. Let's take an example here. Approximate the area under the curve this on the interval 0, 1 using 10 rectangle and 20 rectangles, 2 parts. The partition divide the interval into 10 intervals. So here 10 rectangle, so I have to divide into 10 subintervals. So each of length delta x is equal to 0.1, that is b minus a divided by n. So b is 1 minus 0 divided by 10, that is 0.1 is the what you call width. So our intervals are from 0 to 0.1, from 0.1 to 0.2, so that means equal intervals. And here it is, here in this example. So if I want to find the area, the total area under the curve, which is denoted by a, it is the area of 10 rectangles under the 10 rectangles. So approximately equal to summation from 1 to a f of xi delta x. F of xi means we just give the values of this. So f of 0.1, f of 0.2 we give it, and then delta x is 0.1. So this f of 0.1 we are finding from this function. So they are these. You add up everything 0.33. So this is the approximate area under the curve here, and this we found it by finding the area of 10 rectangles. If you want to do with the 20 rectangles, so again you find the delta x. So b minus a divided by 20, this is the width. So x naught is 0, next one is 0.05, and 2 into 0. And so on. So a equal to, that is the area under the curve, equal to area of 20 rectangle 1 to 20 f of xi. So 2xi square here, we substitute the values here, and then because this you are substituting using this function, and then you have this, and then find the value of this using the calculator. This is what. So what happens here is that if you go on increasing the number of rectangle, you are getting better results. That means, so approximation, what is as n gets larger and larger, an seems to be approaching 1 by 3. That means the area under the curve and area of each rectangle is going to be the same as you increase the number of rectangle. So what is the definition here is that if you want to find the area A under the curve, this is given by this, it is nothing but limit of an as n tending to infinity. That means we are not fixing it for 10, 20. We are increasing it to a very big, large number. That means finding the limit of this is nothing but finding the area itself. Let's take an example here. Find the area under the curve this on the interval 0 to 1. So first we find delta x, 1 minus 0 by n. So this is 1 by n, because here n is not specified, and x naught is 0, x1 is 1 by n, x2 is x1 plus delta x. Like that you find all, and xi is I by n. So for I equal to 0 to n. So from 3.1, that formula here using this, so a equal to an, so f of I by n 1 upon n, and then f of I by n is, use this one, then it is 2i minus I by n minus 2 of I by n square, then we have 1 by n. Then we multiply here, you can take here 2 into I by n 1 by n minus this, and I multiply here, and now here the 2 by n square out, then you just write inside I here, then 2 by n cube out, then you have I square. This you already know, n into n plus 1 by 2. This you already know, n into n plus 1, that I substitute, and I get, this is the final function I get. Now for this, what happens, if you get n equal to 100, you will get, you see, n equal to 200, you will get this answer. If you put n equal to 500, you will get this answer. But I will find the exact answer. For that, I will have to find the limit of an as n tending to infinity. So simplify this. So you multiply and you get this. Whenever you find the limit of any function as n tending to infinity, you divide the numerator and denominator by the highest power of n, that is n square. Divide it, we have this. So as n tending to infinity, 1 by n square tending to 0. So the answer is 1 by 3. That is the answer. So here is the Riemann's what you call sum. So the same thing. So let x naught xn be the regular partition of the interval AB, and xi minus 1, that is the width, delta x is given by b minus a divided by n for all I. Pick the point this, where Ci is any point in the subinterval here, and these are called evaluation point. Then the Riemann sum for this partition and the set of evaluation points are given by this. So here are some examples. List the evaluation point corresponding to the midpoint, and here you need to just use this formula to get this, and Riemann sum for this particular example. So these are the answer for the first part of the video, and this is for this part of the video answers for these. And what we have studied here in this, we have studied two things. One, how sums and sigma notation, and how we find the area under the curve. So with this we end the video lecture number for week 12. Thank you.